Thanks a lot for the invitation to FEM and for you to be here, today. I will talk about cyber physical testing in marine technology, and before that I will talk a bit more with my colleagues about what SynTef is, and because there are quite interesting parallels to make with FEM. So to start, SynTef Ocean, which is the company which I'm working for, and myself. So I will present myself after that. Then I'll talk about cyber physical testing and applications, and maybe open up towards perspectives like how hydrodynamics and cybernetics can be coupled together to solve new problems in hydrodynamics. So SynTef is a big research company, private. It's 2,500 or 2,200 people. Very many different fields of research. So the kind of very distinct aspect of SynTef is that we are working very closely both towards university and to the towards the industry, and in particular with NTNU, who was introduced by Erin just before us. So SynTef was actually created as a kind of spin-off or a valorization company from NTNU. So most of our employees are researchers, and most of them again have a PhD. And then we have some management and also a lot of technical personnel, because we operate quite a large amount of laboratories in very different fields. So we have technical personnel and engineers. Interesting, we have most of our, so it's a private company, but also we have to really win our projects on the open market. So it's not very much that we get as funding from the state every year. It's about 8%. Varies from year to year, according to how much we publish, how many employees we have, and so on. So basically, it's a lot of competition, both at the national level, but also international level, both towards research projects, like EU projects, but also national research projects, but also commercial project consulting. So in SynTef, you have different, so you have a foundation, which is non-for-profit. So all the benefits that we do, they go back into the system to invest into new labs and material and so on. So it's not shareholders, they don't get any money back from SynTef, basically. It's a closed circuit. And we have institutes which are organized under the foundation. And each of them has its own specialty. So typically you have energy, digital industry, you have very different topics. It's extremely broad. And I'm working for SynTef Ocean, and SynTef Ocean is again can be broken into different departments. And it results from the fusion about 10 years ago from different institutes in SynTef. And what was a bit new at that time was that we merged the technology, very heavily technological part, where we looked at marine structures, hydrodynamics, and so on. We merged it with the biology world. So aquaculture, fisheries, and so on, and climate, environment, modeling of environment, and things which are quite close to what FEM is doing, actually. And we serve different markets which are connected to these topics. I'm working in the ship and ocean structures department, and what we kind of are proud about is that we have we operate laboratories which are among the biggest in the world in this class. We have software development, and we also have measurement of full scale on ships and so on. And we do also services, studies, and so on to the industry. So we are very connected in many ways to the problems that we are addressing. And the biggest lab we have as of today is the ocean basin. So some of you have visited it. It's a basin which is 80 meter by 50 meter. It's quite large, and it can go from basically 0 to 10 meter water depth. And you can generate waves from different directions, current, and so on. And this was built in about 1980 to serve the shipping market, like to be able to do maneuvering, and not only test in a straight line, as we had the towing tank before, like very long, but not wide. So here we could do maneuvering tests, but also serve the oil and gas industry, which is extremely important in Norway, which exploded in the 70s approximately. So in the 80s, this basin was built, and as Erin mentioned, the new one is on its way. Beyond that, we have, so as mentioned, the towing tank, cavitation tunnel to look at propellers and actually many other things. Also a laboratory with where we look at oil, typically for modeling oil spills and how they could propagate. We have a lot towards the fishery and aquaculture. So typically robots that can process the fish automatically, and we do research on that. We have a full-scale aquaculture site, so it means that we actually produce salmon at SINTEF because we have a kind of research site which was allocated by the state to SINTEF, and the idea is to do research on real fish farm. And on top of that, we have a plankton center and a quite large structural lab where we test typically flexible risers or power cables and so on, and that are mechanical tests with pressure, with the bending and combined load patterns and so on. So it's a very heavy laboratory infrastructure, which has its cost, and it can explain that you have to put back the money into the system because you have to maintain and develop them. So just now we finished to zoom in. I can introduce myself. I'm French, as you probably have detected from my accent, and studied in Lyon. And then I went to NTNU in Norway and got my master's thesis, and a lot later my PhD in cybernetics, marine cybernetics. And I've been working basically for SINTEF Ocean since the start, with some different activities on the way, mostly research, but also management, strategy, and acquisition of projects and so on. Since 2021, I have an adjunct position as a colleague of Erin at NTNU in the Marine Cybernetics Group, and it's mostly teaching and supervision. And I'm happy to be also a member of STC in FEM since 2023, so last year. So going back to this topic, which was cyber-physical testing. So if we start with the basics, why do we need these hydrodynamic labs? And the reason for that is basically three types of reasons, which are very different. Let's say that once, when you have produced an FPSO, like this first ship, or you are going to invest in a floating wind park with budgets which are the order of billions, it's one more step, like to check that the design is working as it should. So in principle, it should be routine. It should be no surprises. Sometimes it's not the case. Sometimes you just discover things that were not planned. You can imagine if you have been using linear theory and you have discovered that there was no slamming issue, you can discover slamming issue there when the waves start to become huge and so on, and then do more research on this phenomena. And that's one of the steps towards getting good numerical models. So if you want to trust the numerical models that you are going to use in the design or in your description of reality, you need to have at some point experiments, something which connects you to reality. And the best, of course, is to have measurements out at sea. The problem with that is it's expensive, inconvenient, because it's difficult to repeat. You can just not spool back and try again. And that's why we have these basins. So we do tests basically for these three reasons. Quite routine tests for checking that this investment is safe, discovering stuff unplanned, and calibrating numerical models. So what we measure in these models that you see, you have this FPSO, you have a semi here, or a floating wind turbine. We measure typically motions with sensors which are optical, accelerations with accelerometers, and if we have a mooring system, we can measure line tensions, internal loads in the tower, these type of things. Very lot of instrumentation that you can have. For slamming, we have typically either pressure cells or panels, which are a bit bigger. So we did the test of high wind demo, which was the first floating wind turbine. I think it was installed in 2009 in offshore Karmøy in Norway. And in 2005 we did the test for this. And as you saw, it was made with fans, exactly the same fans that we use for offshore oil and gas tests. So basically they generate physical wind, and we were doing like that, and we saw that we had some troubles matching the thrust of this turbine. So we added some winches that were pulling and so on. But basically that was what we could call the first test of a floating wind turbine in like the first way of testing floating wind turbines. So as we have seen from the two previous presentations, which are very happy that we have got such a good introductions to the topic, because it shows just that it's floating wind turbines are extremely complex systems. We have all the wind part, but we also have the response part from the structure, and it's an extremely complex system. And when you get into the lab, you need to basically try to replicate this system as well as possible to see if something happens that was not planned by the numerical model, for example. The issue is that when you produce wind like this, it's very difficult to repeat exactly the same wind twice. Even if you use exactly the same time series of voltage as an input, the wind will never be, if you measure the wind, the location of the turbine, it will never be exactly the same twice in a row. And many have tried to improve that, and considerable improvements have been made, but it's still very difficult to get a good wind field over a large distance that is good for floating wind turbines in a hydrodynamic lab. In a wind tunnel, it's a totally different story, but in an open laboratory like that, it's not that easy. The difficulty you have also is when you need to scale down things. In hydrodynamics, we used fruit scaling, and that's basically giving us how we should scale down all the parameters in of our model. And mass has to be scaled down by the cube of the scale, of the geometric scale, which means that we need to be extremely light, and modeling the nacelle and the blades and so on at this with this mass is complicated. We have also an issue, which is that even if we get the perfect wind and a perfect mass distribution, we'll still have a very wrong Reynolds number. So the proved number is non-negotiable because we have waves. So this one we have to keep it. But at the same time, we have, if we do that, we don't have the right Reynolds number, which means that these blades will not work as intended. So long story short, that's why we developed this method, which is actually based on OpenFast, actually, where we couple in real time what OpenFast tell us is the rotor loads with what we measure in the lab. So the rotor loads computed by OpenFast, they are fed into the lab with what I will come back to, which is a robot. We measure the motions, we send them to OpenFast, which computes the rotor loads, and that goes as a closed loop system. So the wind is virtual, numerical, while the waves and currents, they are physical. It looks like that in reality. So you have this is a test which we have done for 10 megawatt wind turbine some years ago, where you see basically how things go, and you see that here we have a cable robot which applies these loads dynamically while the simulation goes. It's you don't see it on this on the previous video, but basically you have here 6 winches which are located completely far away from the model, which are each pulling on the model in the basin, so that the total load that you apply on the model is corresponding to the one that OpenFast predicts. These winches look like that, and they're connected with these small wires to the carbon fiber frame here. So I won't go into great details on the setup, but it's basically a closed loop system, and you have sensors, you have observers that give you access to some data that you don't have access to with the sensors. OpenFast would be here. And then we'll have an allocation problem, which means that you compute how much you should pull on each cable. You do that with each winches, and basically you are there. So the advantage of this method, which we have developed, I think we started about 10 years ago, maybe 11 years ago with that now, is that the wind field is at least controlled. We could repeat it because it's simply a simulation. And the aerodynamic loads can be also repeatable. So we can focus on what we are actually looking at, which is hydrodynamics and not aerodynamics. We have done as good as we could with the aerodynamic part, but we can now focus on the hydrodynamics. We have solved this scaling issue, which we had with the physical rotors. It's extremely simple to kind of test very complicated scenarios that some standards ask you to check, like change of direction, large gusts, and so on, which would be difficult with the physical wind. And I didn't mention that, but if you use you can redesign the model scale rotor to match better the loads. But first, you need to redesign the rotor, and you need to redesign the controller that works with this rotor. So it's quite a lot of work. And with this method, you simply use the simulation model for the rotor that you have. Challenges is that you need to trust your numerical model, and as we saw, yeah, there is still a lot to do on that front, and that's very interesting. And the numerical model has to be fast, because fluid scaling tells us also that you need to run square root of the scale faster than real time. So if you are testing a scale of 1 to 36, you have to simulate 6 times faster than real time to keep up with the fluid scale in the lab. So that's efficiency constraint in the numerical model. And there is something not kind of scientific at all, but when you are as a company, you need really to maintain a team of people that has competence in very different topics. And they need to stick together and work together, because you can't do anything without the OpenFast model. And knowing the bits and pieces of this OpenFast model, you need to have people that are good in experimental hydrodynamics. You need people that are good in control engineering and instrumentation and so on. So it's you need to have a very good team. So I mentioned offshore wind turbines for this technology, but we also use that on sail-assisted propulsion, which is a very hot topic for the time being, because there is a share of the greenhouse gases emissions which comes from shipping, and they try to really hard to put sails back on the ships to reduce that. So it's very efficient. I'm almost time is almost up, but basically it's not greenwashing. It's something that has been proved to work in the 18th century, so until the 18th century, and it's going back. We can use that for station keeping. So use the same type of positioning system or active system to do station keeping of the floater. I'll come back to that. And we can also use that simply to apply wind loads, but on structures which are not floating wind turbines. So, for example, we are looking at floating bridges, and floating bridges are extremely long. So they cover, when we put it in the basin, they cover the whole basin. And to generate a wind across the whole basin is quite challenging. So we use that type of system to simulate wind loads on floating bridges. This is a small video of the sail-assisted propulsion tests. So you don't see the sails, but they are there virtually. There are 4 Flettner rotors. If some of you know about this technology, it's a rotating cylinder, and they are mounted on a bulk carrier. And the bulk carrier is quite good because they have quite a lot of deck space where you can put sails, which is free. We have tested this ship, and we are working with many partners now to further develop and both the method, but also the sails and the sail models. Oops, sorry. I think I might have destroyed this sharing. Let's see. Yeah, I'm back. Sorry for that. Just to conclude, a bit. So you saw that what I've shown here was simply connecting numerical models with experiments in real time and with a control system. We did that for what we call the substructuring, and meaning that we had a system which was a bit complex, so we just put a line somewhere and you say this is numerical, this is physical. What we are working on now is using this type of technology for learning much more about the hydrodynamic systems that we have by changing the boundary conditions that they are experiencing. So imagine that you are testing this FPSO, so this ship. You want to see what are the forces that depend on the response, typically damping or added mass, and what are the forces that are not depending on response. If you have just a simple mooring system and you run a wave, you will get an excitation and a response and a force, but you don't manage to easily split what is response dependent and response independent. Well, with this technique, we can, by just pushing a button, we can simply change the stiffness of the mooring system or change the damping of the mooring system, rerun the same wave, and then we can do this type of splitting. So it's something that we work a lot with for the time being. One part of cybernetics is also load estimation, so estimation theory, and it's understanding what the loads are, looking at the response, and that's something that we are working on with flexible wind turbines for the time being. Will be increasingly important for the large turbines that are planned, like 22 or 21 megawatts for the future. Last project, which is even funnier, which was a project we completed a couple of months ago, where we worked with the Hywind Scotland 3, which is one of the turbines which are operated by Equinor, where we applied methods in cybernetics to understand to detect any faults in the measurements of the line tensions in the on this turbine, HS3, and based on that, definitely the idea is to go to sensor-less mooring line tension estimation. So let's say that getting the holy grail is to be able to estimate what is the tension in the system without any measurement, because a measurement it can fail, it can be biased. It was heavily biased here, for example. It can be yeah. So you have you try to not install it, you not maintain it, and not dismantle it, and so on. So GPS has to be there for many reasons. So why not using just GPS? bottom line, it doesn't work using only just GPS for this case, but by fusing smartly the different sensors that were on board, we could manage to estimate the tensions and remove biases from sensor and so on. So that was all from my side. I hope I was not too long. No. And that's a kind of artist view of the next basin, so that you are welcome to see next time you are in Trondheim. Thank you.
Very clear presentation. So,
yeah, yes. Yes, Julien.
Well, regarding the software in the loop, I've seen in the past in another voice, increasing noise with.
Okay.
So in particle validation, we have enough matches at those. And when increasing regimes, it just became really blurry and really difficult. I mean, to get anything from the signals really, and was kind of a latest part of the expeditions. We were a bit far away from the experiment, so we make much of it. Have you? I mean, it's been a few years now. Have you? I mean, it wasn't at the same time, but was it? Have you been gathering more experience now in filtering those?
So the noise, you mean the noise was not? Is it like wind loads which were noisy, or was it?
It was in the winches. I mean, the responses in the winches.
Okay.
The numerical signals were a bit.
Yeah, I think I'm not. I mean, I would say that we have been improving since the beginning.
Yeah.
It's a very complex setup, and we have been learning. We are still learning a lot, but it's very difficult to answer like with out of the blue what.
But are you including a lot of filtering on the
filtering is
signals in the winches? I mean,
we try to avoid as much as possible filtering, because filtering means delaying. And it's changing. It might change. Depends on your system and so on, but it might change the dynamics of the. So it's basically to give you the frequencies. We sample and work at 200 hertz, and the filters we apply on the signals. They are for the 4 signals. They are on the order of 100 hertz, so it's no filtering basically, and. I'm not sure exactly, so that's why I'm not sure what you refer to as noise, because what is post-processed, so what's not used in the closed loop, is filtered at 20 hertz. Because typically you have 50 hertz, which is that can pollute the measurement. But yeah, I mean, I have to look at the time series to understand what. Yeah.
So that's okay. I mean. It might have been as well a problem in the experiment or in the way quite at the beginning of the older software in the loop.
Yeah, okay. Yeah. Thank you. Yes?
I'm not an expert, sorry, but I have just one question. I think I understood the approach, and the approach is really good because you can repeat your wind field exactly the same times. But is your wave field still good if you have no winds that apply on the waves?
Yes. So let's say that the wave is really what we are good at. So the waves are really repeatable, and you can actually for this test that I showed with this ship, the FPSO, we ran the first test I think to 2015. And we run the same kind of wave 3 years later, and it was, and we measured it again, and we got the same wave elevation and so on. And of course,
my question is, in your tank, if your wind is just like you pull on some rock,
yes,
but you don't have wind on your waves. So your wave.
Oh, sorry. Okay, so the effect of wind on waves, that's what you mean?
You have to separate completely the arrow.
Yes, that's true. Yeah, that's. that's a very strong assumption of the method. You can say that it's a drawback, but at the same time, I think it can take time to answer that one. But I can just try to be short. When we apply wind loads on a structure with fans, like the big ones, we don't try to match the wind profile correctly, because we know that there is no hope to do that. So what we do is to take the model, the small scale model, attach it into to load cells, low wind with the voltage that we control, and when we get forces or loads which are matching what we have gathered in wind tunnel or by CFD, then we say, okay, this is the right tuning setting for the fan. It doesn't mean that this velocity is the correct one in full scale. It just means that this velocity, this voltage gives us the right force from the wind in the lab. It means that actually it would not give you the right effect on the waves. So this is definitely a limitation, and there are some labs which are also wind tunnels in a way. Wave tanks and wind tunnels, but they are much smaller than this one. So you have other problems. So it's always like you need to find the best compromise to solve your problem. Yeah. Yes. Thanks.
One more question.
I didn't understand the scaling issue when you talked about real time and you say it has to be 1/6 of the net scale.
Yes. So when you use when you go to the hydrodynamic lab, you try to reproduce the waves that you have offshore. And the wave, what is it? Is simply the balance between gravity and inertia. So basically, if a wave particle goes up, gravity will bring it down, and inertia will just make it continue. So you have to keep this balance, and that's fruit scaling. Keeping gravity and inertia loads at with the same ratio at large scale and small scale, that's fruit scaling. When you say that fruit scaling has to be constant, and when you say that that the length have to scale with a factor of 40, then the ratio that needs to be constant gives you also the scaling laws for all other quantities. So the velocity, the accelerations, and the time. So it means that if you want to apply fruit scaling, and you decide that the scaling factor is 1/36, the fact that you choose fruit scaling will force you to scale time with the square root of the scale, with the mass with the cube of the scale, the velocity with the square root of the scale, and so on. So you have all this, which is kind of tabulated and known. If you were trying to match Reynolds number, it would be totally different. So, and for time, it's 1 to the square root of the scale. So 1/36 means 1/6, 6 times faster than full scale. So OpenFast has to be we have to do a lot of work on beforehand to just select the right settings in the OpenFast model to capture what's needed, typically flexibility of the blades and how many modes and so on, while being able to compute fast enough in the lab.
You could also do the simulation in OpenFast with a small scale model, but still you'll need OpenFast to be very fast anyway.
Yes, and then you won't get the right behavior at full. What we are after is the correct behavior at full scale.